Good morning, students. Now we start solid state physics. In that, the today's topic is construction of reciprocal lattice. In this topic, firstly we explain concept of reciprocal lattice, then construction of reciprocal lattice in one dimension, two dimension, and its extension in three dimension. And here we show the animated example of how to obtain reciprocal lattice from direct lattice. To explain concept of reciprocal lattice, we use direct lattice or real lattice. Using the concept of reciprocal lattice, we discuss how a plane in direct lattice becomes a point in reciprocal lattice. This concept was proposed by P. Ewald in 1921. The idea of reciprocal lattice display both characteristic features of the lattice, that is orientation of planes and interplanar spacing. In direct lattice, if the orientation of the set of parallel planes are described by their common normal and the length of the normal relate to reciprocal of interplanar spacing, then it becomes more easier to visualize one-dimensional normal than two-dimensional plane. That point we explain in the next article. The planes far away in the real lattice are closer to the origin in the reciprocal lattice. Thus, by constructing reciprocal lattice, we get all information about the crystal only within the unit cell. Here we discuss about construction of one-dimensional reciprocal lattice. For that, we use direct lattice planes. We consider a set of parallel and equidistant planes which are perpendicular to A axis and it is parallel to B and C axis. Therefore, the Miller indices of these planes are 100, 200 and 300 and so on. We construct the infinite number of such a parallel planes along A axis. Now we choose arbitrary any lattice point as a origin, and from the origin we draw a common normal. That normal for all set of parallel plane is denoted by OP. Along the common normal, we mark the various points, reciprocal lattice points for the plane 100, 200 and 300. These points are R1 and R2. Now we find this R1 is a reciprocal lattice point which is denoted as 100, R2 200 without bracket. Therefore, these are the reciprocal lattice points for the plane 100 and 200. Now we get a new vector. Along we locate the points R1, R2, R3, R4 and so on. That new vector is called reciprocal lattice vector A star. Now we find what is the magnitude of the vector length of the normal for the plane 1, 0, 0. That reciprocal lattice point R1, which is at a distance equal to reciprocal of the interplanar spacing for 1, 0, 0. Therefore, OR1 inversely proportional to D100. Here the constant of proportionality is M, that M is also called as scale factor or magnification factor. Therefore, the magnitude of the length of the normal for 100 plane is equal to M divided by D100, that we call A star. Similarly, to find the length of the normal for 200 plane, we mark the point R2, which is at a distance equal to D200, and therefore this length of the normal, which is at a distance, equal to reciprocal of the interplanar spacing, that is M divided by D200. But 200, 300, 400, which are at a distance of half, 1/3, 1/4, the spacing of 100 planes, and therefore D200 is at a distance of half from 100. Therefore, the equation we write here, M divided by D100 by 2, simplified as 2M divided by D100. That vector is 2A star. Similarly, we find the number of reciprocal lattice points along this common normal. Therefore, for each reciprocal lattice point along A star is, generally we write the magnitude of ORH, that vector denoted by R star H00 or D star H00, that equal to M divided by H D H00 equal to H times A star, where H is equal to 1, 2, 3 and so on. Similarly, we find for other planes which are perpendicular to B axis and C axis. Therefore, we get the new vectors B star and C star. Therefore, we write directly the reciprocal lattice vectors B star and C star are represented as R star 0K0 or D star 0K0, that equal to K B star, where K equal to 1, 2, 3 and so on. This is the reciprocal lattice vector for all set of parallel planes along B star, means that planes which are perpendicular to B axis. Similarly, if we choose another set of parallel planes which are perpendicular to C axis, therefore we get the reciprocal lattice vector for these planes which are drawn from the common origin are R star 00L or D star 00L equal to LC star, where L equal to 1, 2, 3 and so on. That is, for A star axis we get HA star. For B star axis we get new vector KB star, and for C star vector we get LC star vector. Now these are one-dimensional reciprocal lattice vectors. By constructing the various reciprocal lattice points along A star, B star and C star. Here we discuss about two-dimensional or square reciprocal lattice. For this, we choose monoclinic lattice in which all lattice planes are perpendicular to the plane of paper and these are parallel to z-axis. In this figure, we only considering the normal to the direct lattice planes are shown by A star and B star or X star and Y star axis. Now, how we get A star and B star, that we discussing firstly. In the direct lattice planes, we choose any lattice point as a common origin, and from that common origin we draw normal to all set of parallel planes. For example, if we consider the direct lattice planes like 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0 and so on along x-axis, for that plane we draw normal to that set of the plane. That normal is along the A star, is common normal drawn from the common origin. For the plane 1, 0, 0, this is the direct lattice plane that is shown here, and the normal we draw. The length of the normal is OA and it is at a distance equal to m divided by d100 or A star. Similarly, the other plane 200, the same normal coming from the common origin. The length of the normal for the plane 200 is OB. Again, it is at a distance equal to m divided by d200, or we write 2 into m divided by d100. Since 200, 300, these are at a distance equal to half, 1/3 of 100 plane. Therefore, the point A, B, C are the reciprocal lattice points, and all points along a line form a reciprocal lattice vector A star. Similarly, another vector, direct lattice vector, that is Y. We choose the direct lattice planes like 0, 1, 0, 0, 2, 0, 0, 3, 0 and so on. That set of the parallel plane, we draw a normal from the common origin O. Firstly, for 0, 1, 0 plane, draw a normal. That normal is along Y star axis. For 0, 1, 0, the length of the normal is OD and it is at a distance equal to m divided by d010. Similarly, for other plane, that we write the direct lattice plane 0 to 0, the same normal we draw here, and the length of the normal for 0 to 0 plane is OH. Hence, the point at the end of the normal becomes a reciprocal lattice point since it is at a distance equal to reciprocal of their interplanar spacing. In that way, if we join these two vectors along x star and y star axis, we get the resultant along OE and it forms a square lattice. Here for the point E as a reciprocal lattice point, for that we considering direct lattice plane 1, 1, 0, since that direct lattice plane intersect one unit along x-axis and one unit along y-axis. That 1, 1, 0 plane, we draw normal from the origin. This normal is along the direction OE and the length of the normal is at a distance equal to m divided by d110. Therefore, the point E is a reciprocal lattice point. Similarly, the next reciprocal lattice point along the same normal is 220. Next one is 330 and so on. For two-dimensional reciprocal lattice, we choose the reciprocal lattice vector along OE, that is D star 110 or R star 110. It is the vector sum of OA plus AE, and that AE is equivalent to OD. OA is at a distance equal to m divided by D100, that is A star, and AE equivalent to OD. OD is at a distance equal to m divided by D010, that is V star, and therefore the resulting vector OE is the vector sum of A star plus B star, and it forms square reciprocal lattice. For HK0 plane, the resulting reciprocal lattice is R star HK0 equal to D star HK0 equal to H times A star plus K times B star. Now we extend the two-dimensional reciprocal lattice in the 3-dimension. In 3-dimensional reciprocal lattice, we get a reciprocal lattice point for HKL plane. Means that reciprocal lattice point is a result of once it travel H unit along A star axis, K unit along B star axis, and L unit along C star axis. The resulting vector D star HKL becomes H A star plus K B star plus L C star. Hence, the general rule for constructing the reciprocal lattice is that by choosing the direct lattice plane, we find any lattice point as a origin, and from that origin we draw common normal to all set of parallel planes. If we mark a point on the end of the normal, that point is at a distance equal to reciprocal of their interplanar spacing. If we join all the points along that vector, it forms reciprocal lattice vector, and we get one-dimensional reciprocal lattice. Then also we find the two-dimensional reciprocal lattice and then extend it into the three dimension. Here we show the animation of how to obtain reciprocal lattice points from a direct lattice. For that, these are the direct lattice planes and these are the direct lattice vectors along x-axis A, along y-axis B. Here we choose the set of the parallel plane. That set of the parallel plane have the common origin 0, 0. From the common origin, draw normal to this set of the planes. For example, 0, 1, 1, 1, 2, 1, 3, 1, 0, 2, 1, 2, 2, 2, 3, 2. We get the reciprocal lattice vectors A star and B star. Thus, it gets possible to find the reciprocal lattice points from the direct lattice planes. Here, as the index of the plane increases, just like 0, 1, 2, 3 along x-axis or along y-axis, that is 1, 2, 3, then the interplanar spacing between the planes goes on decreasing and the planes start to crowd in the real lattice. That is shown in detail.